Welcome back to Java Internals Crashcasts. I'm Sheila, and with me, as always, is Victor. Today, we're diving into the fascinating world of performance and scalability in concurrent programming. Specifically, we'll be exploring Amdahl's law, a fundamental principle in parallel computing.
That's right, Sheila. Amdahl's law is a crucial concept for understanding the limitations and potential benefits of parallelizing our code. It's going to be an exciting episode.
Before we jump in, let's start with a quick quiz for our listeners. Here's the question. If you have a program that takes 100 seconds to run sequentially and 95% of it can be parallelized across an infinite number of processors, what's the maximum speedup you can achieve? Think about it, and we'll reveal the answer at the end of the episode.
Ooh, that's a great question, Sheila. It really gets to the heart of what Amdahl's law is all about. I'm sure our listeners will be pondering that as we discuss the topic. Without giving away the answer, I think this question will help illustrate the surprising limitations of parallelization.
Absolutely, Victor. Now, let's start with the basics. Can you give us a brief explanation of what Amdahl's law is and why it's important in concurrent programming?
Certainly. Amdahl's law, named after computer scientist Jean Amdahl, is a principle used to find the maximum improvement in a system when only part of the system is improved. In the context of parallel computing, it helps us predict the theoretical speedup in executing a task using multiple processors compared to using only one.
That's interesting. So it's not just about making things faster, but about understanding the limits of how much faster we can make them.
Exactly. It's a reality check for parallel computing. The law essentially states that the speedup of a program using multiple processors is limited by the part of the program that can't be parallelized.
I see. Can you explain how we might calculate this speedup without getting too technical?
Of course. Essentially, we look at two main factors: the proportion of the program that can be parallelized and the number of processors we're using. The law helps us calculate a theoretical maximum speedup based on these factors.
That's helpful. Let me see if I understand this correctly. If we have a program where 80% can be parallelized and we're using 4 processors, we'd plug those numbers into the formula?
That's exactly right, Sheila. And in that case, you'd find that the maximum speedup is less than you might expect. Even though you're using 4 processors, you wouldn't get a 4 times speedup.
Wow, that's less than I would have expected. It really highlights the limitations, doesn't it? Can you give us a real-world analogy to help visualize this concept?
Certainly. Think of it like a team project. Let's say you have a project that takes 10 hours to complete alone. 8 hours of the work can be divided among team members, but 2 hours require your specific expertise and can't be delegated.
Okay, I'm following. So even if we add an infinite number of team members, we can't reduce the time below 2 hours?
Exactly. No matter how many people you add to the team, you can't go faster than those 2 hours plus the time it takes to do the parallelizable work. This is the core insight of Amdahl's law. There's always a sequential part that limits our speedup.
That makes a lot of sense. Now, how does this apply in real-world software development? Can you give us some examples?
Absolutely. In software development, Amdahl's law comes into play when we're optimizing applications. For instance, if we're working on a data processing application, we might parallelize the actual data crunching, but operations like reading the initial data or writing the final results might remain sequential.
I see. So even if we use a supercomputer for the parallel part, we're still limited by those sequential operations?
Precisely. This is why it's crucial to identify and optimize those sequential bottlenecks. Sometimes improving a sequential part can have a more significant impact than trying to parallelize everything.
That's fascinating. Are there any common misunderstandings or pitfalls related to Amdahl's law that developers should be aware of?
One common pitfall is assuming that adding more processors will always significantly improve performance. Amdahl's law shows us that there are diminishing returns. Another is neglecting the overhead of parallelization itself, which can sometimes outweigh the benefits for small tasks.
Those are great points. Now, I'm curious about the limitations of Amdahl's law itself. Are there situations where it might not apply?
Good question. Amdahl's law assumes a fixed problem size, which isn't always the case in real-world scenarios. For problems where the workload increases with more processors, like in some scientific simulations, we might see better scaling than Amdahl's law predicts. This scenario is better described by Gustafson's law, which is sort of a complement to Amdahl's law.
That's really interesting, Victor. It sounds like understanding both Amdahl's law and its limitations is crucial for making informed decisions about parallelization. Do you have any final tips or best practices for our listeners when it comes to applying Amdahl's law in their work?
Absolutely. First, always measure before and after parallelizing. Amdahl's law gives us theoretical limits, but real-world performance can be affected by many factors. Second, focus on optimizing sequential parts as much as parallelizing. And finally, consider the problem size and whether it might grow with more resources, as this could change your optimization strategy.
Those are excellent tips, Victor. Now, I think it's time to reveal the answer to our quiz question. Remember, we asked, if you have a program that takes 100 seconds to run sequentially and 95% of it can be parallelized across an infinite number of processors, what's the maximum speedup you can achieve?
Ah, yes. Let's see how our listeners did with this one.
The answer is a speedup of 20 times. Using Amdahl's law, even with 95% parallelization and infinite processors, we're still limited by that 5% sequential portion. The maximum speedup is 20 times faster than the original.
Great explanation, Sheila. This really drives home how even a small sequential portion can limit our overall speedup.
Absolutely, Victor. To wrap up, we've learned that Amdahl's law is a powerful tool for understanding the limits of parallelization. It reminds us to focus not just on what we can parallelize, but also on optimizing sequential portions of our code. In our next episode, we'll be discussing contention and coherence in concurrent systems. Thank you for listening to Java Internal's Crashcasts.
And remember, if you enjoyed this episode, please subscribe and leave us a rating. Your support helps us continue to bring you deep dives into Java internals. Until next time, happy coding.